So we provide the recommender system with user preference data as input. The user preference data is actually quite simple. It represents what users like and dislike. These preferences may be of two forms. They may be explicit, in which case we're simply asking users what they like or dislike. So like Netflix star ratings of movies you watch, you give it a star as an example, or TiVo thumbs up or thumbs down ratings, or we ask them, how would you rank these items? On the other hand, they may be implicit. We observe the behavior of the user to determine the preferences. If it's music, well, which artist does a customer listen to? And how frequently does a customer listen to that artist? And how long does it listen to that artist? And does the customer move an artist up or down in the queue? So again, implicit is behavior. We observe behavior. Explicit is we ask the user. So let's look at an example here of a matrix of users and item interactions. And in this case, on the y-axis, we have artists, and on the x-axis, we have users. And each element of the matrix are the number of times a user played an artist. So we could clearly collect this data in our apps. Every time the user plays an artist, we just increment the play count for that user. So neighborhood-based recommendation systems take this information and look for similarities between users. They look for users with similar preferences. So, Betty and Dave played similar artists. They had these three overlapping. And Dave also played Taylor Swift, so maybe we want to recommend Taylor Swift to Betty. So we're taking these and making recommendations. Now, how exactly do we do this? Neighborhood-based recommendation systems, similar users, we need to calculate, say, the distance between these two users. If users are in the same neighborhood, they have a similar set of tastes, then we can recommend the items that they like to other users in that neighborhood. And there's different ways of doing this. Different metrics can be used for the distance. And oftentimes that similarity metric is a key consideration for the type of recommender, and we may want to experiment with it. For example, let's say we had, rather than implicit numbers here, let's say we had explicit ratings from users. We asked each of these users to rate these artists as they played them. Oh, do you like this artist? On a scale of 1 to 5. Then we could use a similarity metric of Euclidean distance that simply finds the distance between users for each of these items in common. If Dave and Betty both gave ABBA a 5, then they're in the same neighborhood with respect to ABBA. We can compute the distances between users to find similar users and then make recommendations. Now let's focus on latent factor collaborative filtering. In contrast to neighborhood-based approaches, we don't need to worry about something like the distance between two users' preferences. Instead, we give the model the data and tell it the number of latent factors that we would like to use, and the model determines the latent factors. These factors for the users and the items then determine how much a particular user will like a particular item. To summarize, you provide the data, the algorithm determines the latent factors from your data, then you use the latent factors to make recommendations. Let's look at an example. Consider a latent factor model where we've been able to interpret two tastes as psychedelic rock music from the 1970s with blues guitar undertones and Swedish dance music with female vocals from the 2000s. Artists that would have high appeal values for these tastes would include Pink Floyd, Led Zeppelin, and The Doors for psychedelic rock, ABBA, Icona Pop, and Taylor Swift for Swedish dance music. The appeal of these artists to each taste can be represented as vectors. Pink Floyd might be valued at 0.9 on psychedelic rock music from the 1970s and 0 on Swedish dance music. Taylor Swift, on the other hand, would be rated 0 on psychedelic rock and perhaps 0.6 on Swedish dance music with female vocals. Her newest album was produced by a famous Swedish pop producer and likely appeals to similar tastes. While we are giving an example here with specific factors, latent factors are not easily interpreted like we're showing above. We cannot articulate them. The algorithm will find them, but we will never really know what they are. This is not a content-based approach where we do explicitly characterize users and items with a set of attributes. Instead, the algorithm is capturing some complex facet of the domain and expressing it in an abstract factor that a group of items have in common. Here we've plotted the two item latent factors that were crudely interpreted. Note how Iconopop and ABBA have high values for latent factor 2. Taylor Swift has a reasonably high value as well. Pink Floyd and Led Zeppelin both have relatively high values for latent factor 1, and Iron Maiden is up there as well, showing that it has some appeal in the dimension that is being captured by the latent feature as well. Now let's look at the tastes of two users, Alex and Dave. Alex really likes psychedelic rock, but not Swedish dance music. So the vector representing his taste is 0.9 and 0. Dave, on the other hand, likes recent psychedelic rock and loves Swedish dance music, so the vector representing his taste is 0.4 and 0.9. To determine a user's preference for an item that they have not interacted with, you simply multiply their user factor vector by the item factor vector. For example, to determine Dave's preference for Taylor Swift, we multiply Dave's vector by Taylor Swift's vector and get 0.54. Taylor Swift provides Dave nothing to satisfy his slight preference for psychedelic rock, and 0.6 to satisfy his high preference for Swedish dance music. But remember, in spite of our example, these latent factors are never made concrete. They are latent. To generate these recommendations for users, we need an algorithm to determine latent factors. In an upcoming chapter, we will see the ALS algorithm in Spark's machine learning library, MLlib. Finally, let's step back and look at the I/O and processing structure of recommenders. As input, a recommender takes a user and item matrix of implicit or explicit preferences. Recall that implicit preferences are observations of a user behavior, and explicit preferences are explicitly given by a user. This matrix is going to be a sparse matrix. A recommender produces a list of items along with a predicted preference for each. From this output, we further remove items known to be of little value, sort remaining items in descending order of predicted rating, and then somehow present this to the user in the application.